continuously improving the driving agents, making better and better driving policy so that we can create, a useful ADAS experience by using modern machine learning to train better driving policies. So part of the way that works is we have extremely tight integration between, the research of actually trying to develop better driving agents and then the product, which is OpenPilot. All of the experiments that we run, if we feel comfortable that this is a worthwhile experiment and all of our offline testing and simulation testing looks good, it goes directly to a branch in OpenPilot, which by definition is public and everyone can see it. All the data that we use to train all of our models comes directly from our users in the fleet, and everything is trained in a local data center that you can see in the picture here. It's a modest data center in our own building that's paid for by the users. And then we train models on that data center in-house to improve the product, to fund a better data center. So it's a very tightly coupled loop. We get the data from our users, the users fund the data center and the research, and we make better product for them. Got about 6,000 daily active users, and then a lot of those users directly upload the data to us. So because of our resource constraints, and we have a relatively small team, to make a genuinely good driving agent, we want to make a solution that scales really well with data and compute, and not one that scales with engineers, because that's expensive. So we want an end-to-end approach, one that goes directly from sensor inputs, in this case vision, to an actionable plan, and that can be inspired by human driving data to become better and better. Because of our user base, we have extremely diverse data from more than 50% of the countries of the world. We have over 200 million miles of data, and those users, by and large, drive relatively well. Humans are relatively good drivers. And even if you want to make a driving agent that's better than the average human, there's some subset of human driving data that is, vastly superior to the average human driver. So we can get good human driving policy just being inspired by actual driving data from humans. So the goal is, how do we take all of that driving data that contains at least some subset of superhuman driving policy and distill that into OpenPilot so that we can make a useful ADAS product? I think one of the guiding principles that we use when we develop these methods is Rich Sutton's bitter lesson, where he talks about the power of general purpose methods that continue to scale with increased compute and, in our case, also data. I think that's something that should probably be added to that. So I'll give a quick timeline of what happened for us to get here to today's paper. OpenPilot was started in 2015. At the time, it was a very simple experiment that just detected lane lines and then sent some control signals to stay between lines. And then in 2016, we kind of outlined a strategy that we wanted to train in learned ML simulation so that we can do on-policy training under the assumption that on-policy training is necessary to react to all sorts of situations that can happen on the road. 2016 is a long time ago. That's almost 10 years ago now. And it took almost 5 years before we made some significant progress on this trajectory of shipping end-to-end policies to users that create a useful product. So in 2021, we had our first real success. We had a driving policy that was entirely trained end-to-end. It decided where to drive, decided how to steer, without explicitly ever referencing any costs like staying away from lane lines, staying away from obstacles, staying away from cars. It was entirely learned to mimic human driving behavior. We shipped that into beta testing. Then with enough validation and more improvements, we ended up shipping it to release. So this is what users have been driving with our 20,000 users for the last few years. In 2022, we ended up doing the same things for longitudinal control. So we made a policy that stops at red lights, stops at stop signs, slows down on exits, all those things without ever having been taught any of those rules. Nowhere in our stack do we reference stoplights or stop lines explicitly, yet that behavior is distilled pretty well. In 2022, we had a demo of this where we also included navigation inputs, so just a map of where to drive, and showed that we could drive point to point to Taco Bell with this complete end-to-end stack. And then in 2023, we sent the longitudinal end-to-end policy into beta testing, where it still is today. And then in 2024, we started working on training in world model simulation. So that's what we're talking about today, where instead of using classical simulators that have all sorts of flaws, we can use a world model that is much more generic and scales much better with data to simulate the diversity of scenes that is necessary to capture driving. There's been a lot of people talking about the necessity for that today, so I don't think I'm preaching to the choir with that one. But I'm going to hand it over to Yassine, where I'll talk about some of the details, how we ended up successfully having an experiment with that, and also shipping it to real users and demonstrating that it can be a useful ADAS product.
Yeah, so the word model that can take you to Taco Bell. Um, so if word models and simulators are the buzzword of today and of this year for self-driving, end to end is also a big topic. So, I mean, yeah, it's pretty easy, right? You just collect a big data set of driving video, and we have that. We have a lot of data, a lot of users. Sensor readings, you parse all that stuff. You train a model that inputs the images, and then you predict the curvature of the steering wheel on the acceleration on the pedal. Um, Looks easy, right? And then more data, more compute, better driving, everything's great. You profit. Um, well, unfortunately, that doesn't work. We've heard about why it doesn't work before, but I'm going to give it a uh, little overview of exactly why. So, um, the problem with imitation learning or of policy training or offline learning is that when you have these IID assumption of training in a training data set, and then when you deploy the model, the mistakes that the model makes will influence its future observations. So the errors will accumulate, the observations will no longer be IID, and you put the model in a place where that they've never seen actually in the training data. So it won't learn to recover because it's never seen problems like that in its training data set. And there are tons and tons of research about this and how to mitigate it. One way to mitigate it is to actually train what we call on policy, but some other groups would probably call it like closed loop or off policy with interactions with the environment. Different terms can mean slightly different things, but essentially you collect a data set, you collect data where the driving model actually interacts with the environment in closed loop. And then this data set is now called experiences or rollouts, and it will include the mistakes that the model makes, um, but it should also include the corrective actions, or how do you actually recover from those mistakes. So these are two different things that your data set should include, or maybe a reward function, but that's hard to make. We all know it's impossible to write a good reward function. Um, so there's a few ways. There are a few ways to do this, right? Um, you could do this in the real world, and some people did it. The first image top right is a video of Wave.ai, and they essentially learn how to drive straight in a day in a field. And it took them a day to learn how to drive straight. So it might take a little longer to drive in more complex situations. Another way to do it is to use a classical simulator. So something like, game engine or something that you write in house. The middle photo is from Tesla AI Day 2021, where you can see a big, I don't know what animal is that, a moose crossing the road. So yeah, you need a lot of work to make the simulator diverse, and you're essentially transferring the work from making a driving agent to making a simulator, and that's also hard. And another way to do it, and what we think is the best way, is to use a data-driven simulator. So a simulator that is based on data that you collect, and that by definition is diverse because you can collect tons and tons of data from anywhere in the world, and also very cheap. And our paper uh, shows two ways to do this. One way is a kind of a baseline, which is based on like 3D geometry reproductive simulation, and then the other way, which is a little more interesting, which is based on a learned world model. So a reproductive simulator is essentially just null view synthesis using a depth map and just simple 3D geometry. So if you have a few images and if you have a depth map, you can just reproject the pixels, use previous and future frames, and use some checn and things like that to impede things that are moving and to impede things that are occluded. It's very standard, and a lot of tricks are required to actually make a realistic image and avoid the limitations. What are the limitations? So first of all, because we use a depth map, we assume that the scene is static. We assume that things around you don't move, don't react to how you move. Let's say you swerve into a car, you can't really write code that will make the car swerve next to you, so it doesn't really handle counterfactuals. Your depth map is going to be inaccurate. Um, yeah, difficulties with occlusions and in painting. Because we only reproject pixels, there's no lighting model. So at night, the pixels that you're gonna reproject are not gonna take into account the lighting factors. Uh, and all these problems lead to artifacts. And these artifacts are usually correlated with how you wanted the car to move, which leads to what we call cheating. And cheating is essentially when you train a model in this simulator, and I, I say again, we want to train a model in this simulator, not just evaluate it. When you train a model in this kind of simulators, they will use these artifacts as shortcuts to learn how to drive. We'll use a word model simulator now instead of just 3D geometry. So this is standard diffusion. Everybody's using diffusion models right now, so I'm not going to spend a lot of time on it. It's a transformer. It's a stack of essential layers that we essentially adopted to video instead of just generating one frame. Um, and this transformer is conditioned on vehicle positions, and then time and noise levels. So it's pretty standard now to do these kind of things to add more and more conditioning to diffusion models. Um, and it's also what we call future anchored, and I'll talk about that a little later. But that's a very, very important aspect of our world model. We train it using a very simple loss based on the rectified flow formulation, and basically the world model generates not only the frame but also generates a trajectory of where the car should drive in the next few steps, essentially. And we have the standard tricks to avoid what people call auto regressive drift, and standard tricks to capture the multimodality of driving trajectories. So all very standard, all very simple diffusion model that generates a frame, given a history of frames and given a history of actions, and tells you where to go. We showed that this model can scale well, more parameters, better performance, more data, better performance is what we want. Good stuff. And this is what you get. You get good looking video of driving. And yeah, this is a few scenarios of the world model imagining driving scenes. This is a 500 million parameter model, so it's very small compared to like, Sora or Neo 3, the multi-billion parameters. So yeah, these are a few examples. I'm not gonna spend a lot of time showing you guys this because it's pretty standard now. We can also control these world models using position. So in here you can see how in the top video, we just let it go straight. In the middle video, we make a right deviation to the deviation to
Hi
the right
everyone,
of,
I'm
half
Chen.
a
I lead
meter.
the perception team at
And
Waymo.
then the bottom one, it's a left deviation.
In the
of
past
half a
year,
meter.
Waymo has made a significant progress in terms of the number of trips that we serve.